Today we're going to talk about something called the steady state approximation. And basically, while a catalyst can appear in a rate law, an intermediate can't appear in a rate law. That's something you just kind of have to kind of wrap your head around. One of the problems that you're going to do early on, involves catalysts in rate laws. But under no circumstances does an intermediate ever appear in a rate law that we write. So I have this reaction for us here, and this is the breakdown of ozone into 3 oxygen here, and this is the proposed mechanism. It has a fast step and a slow step. And just looking at it, the first thing I want to check is to make sure that the overall reaction meets the proposed mechanism. So I see that this O is an intermediate because it is made, it's produced in the first step and consumed in the second. And so that goes away. But when I add up, I have 2O3, and then I have 3O2. So from that standpoint, we're okay. These two add up. There's 2O3, there's 3O2. That matches my overall reaction. But my problem I run into is when I go to write the rate law. I have an O3 there, but I also have that O. So when I go to predict, it would be K rate equals K O3. That's not acceptable, okay, because it would have an intermediate in it. So what I have to do is I have to go back up into a reaction, and I have to look at that fast step and isolate the O, okay? So essentially what I would do is I would create something that looks like this. All right, so I take the rate, because you see how this one has the back and forth arrow? That's because that reaction goes back and forth really quick, and we would assume that those rates are going to be inverse of one another. Now, we don't really, being that this is a first year chemistry class, you're not going to get too deep into the weeds here, but essentially what you need to realize is we're going to kind of disregard the rate constant here, although we are going to divide both sides by K prime, and then we're going to take also the O2, okay? And when we do that, see, what we did was we divided both sides by the K prime, both sides by the O2, and that gets O by itself. Now, essentially, we're not going to worry about the K's that much, because the K is going to come into the overall reaction that we're going to write, or rate law that we're going to write for sort of the overall reaction. So just think about all the K's getting bundled in together. But what is important when you kind of get rid of the K's there is we have O3 over O2 yields, or not yields, but equals O. So I can plug that in right here, okay? Oh, actually, I want to plug it in right there because that's the slow step. Don't plug it in the fast step, plug it in the slow step. Okay, so I can plug that into the slow step. And so I have now rate equals O3 over O2 times O3. And so I have 2 of those, I multiply them together, and so that is O3 squared over O2 and that is how you do a steady state approximation. Essentially, what you're doing is you find the intermediate and then just rewrite the fast step to look like the intermediate. Just make two little rate laws out of that fast step, isolate it, plug it in, and you're done.